Hi, today we are looking at doing a hypothesis test for a known value. We're going to look at the question, is the average birth weight of babies 7.5 pounds? We're going to assume we took a random sample of 36 babies, and our first step is going to be to create the two hypotheses that we need. The first is H0 or H0, as it's sometimes called. And this is called our null hypothesis. And we have the little letter U here, and it's read mu. It is our population parameter, and it stands for the mean of the population. So we're saying the population mean of all babies' birth weights is 7.5 pounds. And again, we got this value from a known value by looking up on the internet that says the average birth weight of all babies is 7.5 pounds. Now we're testing that against the alternative hypothesis that the average birth weights are not 7.5 pounds. So we're using not equal to. Now the not equal to is a two-tailed test. Now keep in mind that you decide here whether to use a two-tailed test or a one-tailed test. A one-tailed test would be a greater than or a less than, not based on your data. You always decide that ahead of time based on your question that you're asking. So if you were, for instance, asking if maybe birth weights have decreased now that we have more multiples and better technology and using more infertility treatments, that birth weights have decreased because of this, then you might want to use a one-tailed test and look to see if birth weights have decreased because of this, and you would use a less than. So your decision here is based on your question that you're asking. We're just asking if the birth weights of this sample are different from what we know to be the actual value, so we're going to use a two-tailed test. Step 2 is to collect our data. So we go to these 36 randomly selected babies and we write down their birth weights, 7 pounds 4 ounces, 6 pounds 3 ounces, and we make sure that we convert their birth weights from pounds and ounces to decimals by taking the ounces, dividing it by 16 so that we get an accurate decimal. Since this is in decimal form, we need to make sure that this matches and is in decimal form. So for instance, 7 pounds 4 ounces is 7.25. We enter that all into our calculators, and I'm assuming that you know how to put that into, say, a TI-84 calculator and run statistical analysis, or into a computer and get your summary statistics, which is what we want to do for step 3. So step 3 is to calculate our summary statistics. Summary, stats. So our summary statistics, we're going to have X bar is equal to 7.32, S is equal to 0.87, and N is equal to 36. Now keep in mind that these values here are our sample values. S refers to the sample standard deviation. Sigma refers to the population standard deviation. So we don't want to get the value off our calculator for sigma. We want to use the sample values. X bar is the sample mean. So take all of the sample values off of your calculator and use those. So we write down those 3 summary statistics for step 3. And then step 4 is to look to see whether or not, I'm going to move this back just a little bit here. Step 4 is to look and see if how close is X bar to mu. Are they far enough away to say that they're different? Are they close enough to say that their variation is simply due to the fact that we have a sample and a population? So how do we do that? We do that by calculating the Z-score. The Z-score measures how many standard deviations these two things are away from each other. So the Z-score is calculating by taking your sample mean and subtracting off that known value that we started with, the mu from the hypothesis tests that we set up in step 1. We divide it by S over the square root of n. This down here is the standard deviation for our sampling distribution, and this allows us to assume normality and use the normal curve. So if we do that, we have x bar is 7.32, subtract that 7.5, it's our known value, and we had calculated S to be 0.87 divided by the square root of 36. We do that, we get negative 1.24. So this means that these two items are 1.24 standard deviations away from each other. And x bar is smaller than mu, and that's what the negative means. It simply means that x bar is below mu. So let's erase again, and let's draw a picture of what this looks like. So in step 5 here, we're going to examine this value here. So we have z equals negative 1.24. And if we draw a normal curve, which we're allowed to do because the central limit theorem applies, and it applies because our n is greater than 30, and we used the central limit theorem. And here's our 0. And remember that in a normal distribution, there's normal variation here that we expect a sample can fall. That anything between negative 1 and positive 1 here, that's basically considered within normal limits. So if this had been 0.95 or negative 0.96 or 0.83, then I would have immediately known that that's just absolute normal variation and I'm fine. When I get outside of the ones, that's where I have to start checking to see whether or not it's enough to say that these two things, that the x bar and the mu are differ or not. So I am actually, instead of being there, I am, it's probably a little closer there, right here at negative 1.24. So I want to calculate the area here. The area from negative infinity up to negative 1.24. And that is going to tell me my p-value. And my p-value is going to tell me my decision about the results of this hypothesis test. So step 5 is to calculate this p-value. So we're going to continue step 5 on the next page to give me a little bit more room to calculate this. So in order to do this, I have to use NormalCDF. NormalCDF is my way to measure that area. And I'm going to go from negative infinity to negative 1.24 because that's what it showed me on that normal curve. I want this area here from negative infinity to negative 1.24. If negative infinity can't be entered into your calculator, you can use some really big number here like negative 10,000 or something, because once you get to negative 3 standard deviations, you're already way out here. So any number like this is going to be, the area is going to be so small, it's going to not matter at all. So if I do that on my calculator, I get 0.1075, which is approximately 11%. So that means the probability of making a type 1 error is 11%. Or the probability that I reject the null hypothesis when I am not supposed to is 11%. Usually you want your p-values to be under 10% at least, if not 5%. So in this case, because it's 11%, we're going to make our final conclusion to step 6, conclusion. We're going to say since p is greater than 10%, we're going to fail to reject H naught and say there is no significant difference between X bar and mu. Or in other words, there's no significant difference between our average birth weight in our sample and the known value. I don't have enough evidence to say that. Thank you very much. Hope you enjoyed the lesson.